All right, it's my pleasure to introduce Barry Brumitt, a Googler from our Kirkland engineering office, and he's going to be talking about using MapReduce on large geographic data sets.
Play along. It's part of the fun. Put one hand up in the air. If you're from Seattle, put your hand down. If you're from Washington State, put your hand down. If you're from the Pacific Northwest, put your hand down. If you're from west of the Rockies, east of the Pacific, put your hand down. If you're from the US, put your hand down. Anybody left? Where are you from? Thanks for coming. I was just curious. And another question, who here writes code in C++ ever? Python? Perl? OK, pretty CSE crowd. Neat. And one more quiz I have for you is this. So what is this? No, this is MapReduce. And what's this? It's in parallel. OK. Anyway. That just kind of happened in the last session, so bear with me. Anyway, I'm one of the people who has been using MapReduce for all sorts of things that they had no expectation of using MapReduce for. And I'm going to talk about that today, because it's been a tool that's made it possible for me to do a lot of really cool things working on the Maps project at Google. While I've got this map up on the screen, I thought I'd show this off, which is where the new office is in Seattle, which is on the other side of that bridge. That makes me very happy. One thing we do a lot of at Google is processing really large data sets. And by large, I'm talking like hundreds of gigabytes, terabytes of data or more. And if you're trying to actually serve this data up to people in any sort of reasonable way, you can't be going through the raw, unindexed, just kind of bare form and trying to figure out the answer to their queries. It's impossibly slow. So a really common task across many, many Google properties is taking that data and transforming it into index files. Someone recognize that thing in the middle? That's how card catalog. It's like records. And once we have index files, then we load those up onto servers, usually in RAM, so that we can actually answer queries from users. It's really not that useful to have things that are even used slightly frequently on disk, because you're limited by the bandwidth to the disk and the number of seeks you can do. So you can do maybe 100, 1,000 queries a second on a disk. But if you're Google and you're answering the kind of queries we are, that just doesn't do it. So a lot of work actually has to go in to making these index files be something sensible. And MapReduce is a tool that makes that work really well. Jeff talked a lot about MapReduce earlier. In some ways, I'm sort of bummed about that. In other ways, I think of it like teaching math, in that you have to repeat the same things a couple of times before people get it. So just think of this as like a refresher, or perhaps more a drill down into some more specifics. So choose your cast as you like it. So I'm going to think about map data. Map data is big. It's not big like all the web pages in the world big, but it's still pretty big. The North America has on the order of 100 million roads in it. So you can just about get that in memory if you really have to, but you don't want to. Not certainly with all the geometry and all the other data that goes along with it. So when working on maps data, we've got this big, huge, massive set of files that basically describes everything, kind of. Roads, parks, counties, streets, cities, country boundaries, intersections, and so on. And they aren't really organized like a database, because you need a really large database. And it's kind of a pain to have those formal tables. And we just don't really operate that way. It's sort of two different ways of looking at how you organize data. You can either make it super, super structured and build really big tools that work on this structured set, like the SQL server. Or you can operate like in Unix land, where you have flat files with text in it, and you write little tools that are, don't process a very complex file type, but can do something useful with it. So if you think about this map data, you can imagine if you wanted to build a graph, nodes and arcs that represent the road network, you've got to somehow go through this large set of map data and gather the right bits of data together. They're not sorted geographically necessarily, and they're not like attached to each other, because otherwise every intersection or every road would have to be attached to every intersection that it is involved in, and that would be a huge blow up of data. So you've got just this road, and you've got just this intersection, and somehow you'd like to take this intersection object and attach to it all the roads, so you can then have this graph, so you can do things like say, compute turn angles, or figure out how much traffic is there, or do whatever you need to do in this network. So I'm going to propose an algorithm to do that. And of course, yeah, it's going to be MapReduce, but I'm going to go at it sort of backwards. So you could go through this feature list and look at each feature. And every time you see a road, you emit the road as a key value pair, where the key is the ID of all the intersections that it's a part of. And the value is a copy of all the road geometry. And whenever you hit an intersection, you can emit a copy of the intersection keyed by its ID. Then, if you were to sort that list, you'd have grouped together by the key all the things at each intersection, all the roads and the intersection itself. And then, say if you got all that data into one function, you could emit an object that corresponded to a node in the graph. And your problem would be solved. You would have gone from this list thing to this more compact, just graph representation. Still a list, but nevertheless, it actually sort of encodes the graph more directly. So this is, surprise, MapReduce. So if you look at it in this sense, the map function is the thing that runs down that list and emits key value pairs. And so if you look at the road numbered 5 across the middle, for instance, it's emitted twice, both intersection 3 and intersection 6, so that 2 copies of it come out. And each of the intersections is emitted once, and all the other roads, I guess, are emitted once as well. And then this fast shuffle phase happens, which sorts these key value pairs. And so you get all the intersections labeled 3 in one place, all the intersections labeled 6 in another, and then reduce is called on each of those sets of things with the same key, and that emits the object at the end. So you end up with a sorted list by ID of all the nodes in the graph. It's pretty neat. It's a little more interesting than counting to be or not to be, I think. Sorry, I just think I just slammed my boss or something. But the point is that this is a fairly listy kind of operation. It kind of looks like something you could do with a database pretty simply. There's probably a select statement you can write that would kind of do the right joins and stuff. So it's, in some ways, it's not that exciting. You can make the very fair argument that why don't we just build a big database and kind of go at it that way. I mean, there's all the fault tolerance and the scaling and stuff, but you could imagine doing that. The thing that's really neat about MapReduce is it is being used for so many things that the folks who originally wrote it didn't expect it to be. Just to give you an idea of how straightforward it is to use MapReduce, here's a little code example of implementing the thing that I just showed you. Basically, your mapper class has, it takes an input, it's a feature, it turns it into the right type, it looks at what it is, does a couple emits, and it's done. That's like 8 lines of code. The reducer gets a list of all those objects. The first one's going to be the intersection, and then it loops through all the other ones, attaches them all onto the object, and then emits it. It really couldn't be much simpler. And this is why all those interns can check in all this code that runs on huge sets of data on thousands of machines, because that's honestly all the code it takes. I mean, there's some type definitions, you need a little chunk of thing to say how many machines you want, what data center you want to run in, it's a little bit of overheady stuff, but honestly, 30, 40 lines of code, you're running on thousands of machines at once. That's cool. And you can do more than just this like list processing kind of stuff. I mean, list processing is great and all, but you can actually do distributed rendering using MapReduce. You've all used Google Maps. Anyone use Google Maps to get here today? Yes. OK. The way these map tiles can be rendered is if you know how you're going to break up the world ahead of time, you can know sort of which bucket every feature needs to fall into by, say, its lat long coordinates or whatever. You might need to do some overlap to make things render nice or whatever, but for simplicity's sake, you can imagine that you can figure out what bucket for any feature where it needs to land. And so you can look in the map phase at each feature, look at its geometry, look at the set of buckets you're trying to render, and emit a copy of the feature keyed by the ID of every bucket that you want to render in. So for instance, I5 gets emitted to both a north and south bucket. Imagine we're just rendering 2 buckets for the Seattle area. 520 gets rendered into the only the north bucket, I-90 into the south bucket. And I said rendered. I should have said emitted there. And then the shuffle happens, so all the norths get grouped together, all the souths get grouped together. And then in the reduce phase, all the rendering can happen. We just distributed rendering across thousands of machines. We're processing lists. We actually are generating now this huge sorted set of graphics without actually having to worry about any of the communication, any of the fault tolerance, any of the scaling. It just all kind of happens for free under the covers. And that's the thing about MapReduce, is it seems to be applicable to a large, large, large set of problems. So actually, I stole these from Jeff, so I'll just keep going. You can actually process different data types with MapReduce as well. And we've talked mostly about lists of data, but obviously there is going to be some listiness to it because it reads things sequentially through a set of stuff. But you can actually operate, say, on a graph as well. So let's imagine that you had the problem that you wanted to mark all the nodes in the US with the gas station that's within 5 miles. Okay, so you could start by knowing where all the gas stations are, like the red and the yellow one that's up there right now. And then in the map phase, you could do a Dijkstra search out from each gas station, sort of one Dijkstra search for each gas station. And it could go out to, say, a 5-mile radius and emit for every node it touches, let's see if I get this right, the ID of the gas station and the distance to the gas station, keyed by the node ID. And so you can repeat this for all the gas stations in the world. And then it would be sorted, and each node would collect information about all the gas stations that were in 5 miles. And then the reduce function simply looks through the list of gas stations that it's found, finds the closest one, takes the min of all those distances, and emits that to produce the output. And so you've just marked a graph with all the closest gas stations in the world, all the closest gas stations. I think that's pretty neat, too. I mean, there has to be some cleverness here, because the graphs have to live on disk somewhere, and you have to be able to read it. So you can imagine a big table-like object that lets a node that's MapReduce that's processing one node read in all the nodes that are nearby in some sort of efficient cached way. And you can imagine that if you were clever about it, you'd process lots of local nodes on the same reducer, on the same mapper, so that it wouldn't have to go to disk so often. So there are lots of tricks you can do to make MapReduce more efficient. But when you're trying to write really complex MapReduces, that becomes the game, is how do you handle the I/O if you're trying to not work with just a single object and you're trying to work with a whole bunch of different stuff. One thing I didn't say earlier, which is worth repeating now, is the basic reason that fault tolerance works in MapReduce is because every single map operation is completely independent from every other one. It just simply doesn't matter what order they're done in. If one fails, it can be just done again. And the master, much like SETI at home, can say, oh, look, map 12 hasn't been finished yet, so I'll do another one of those, and then it comes back and it all works out. And the shuffle phase is dependent. Like, it has to wait for all the mappers to finish before it can truly close the shuffle. And then the reduce phases are likewise completely independent. If anyone fails, you can just start over and do it again. And that's what gives it this killer fault tolerance. But you have to be kind of smart about it. You want to make sure you break your tasks up carefully so that you don't end up with, say, 32 machines running your 32 reduce tasks, and each one takes an hour, say. Because then if one of your reduce tasks fails at, say, minute 59, you have to wait another hour for that to get finished. So you have to do some smart engineering to think about how to break your problem up into the right size chunks so that you don't end up with this problem of trying to do a huge chunk of processing at once. And sometimes that's easy, and sometimes it's hard. Jeff covered a lot of these. There are a couple things he didn't catch, though. I don't think he mentioned data compression. So when you're trying to transmit data between mappers and reducers, sometimes it's faster to compress it before transmitting across the wire. No big surprise, but it's a good idea. And I haven't mentioned GFS at all, because really, when you use MapReduce, you almost don't have to worry about GFS. It just kind of takes care of all these problems for you. So it's reasonably robust and requires not too much work on the part of the programmer to get good at it. Another cool feature of MapReduce is that you can run it locally as like a single thread. So if you've got some complex reducer, say that map tile renderer that's crashing when it renders something, you don't have to go connect to this cluster that's across the Atlantic trying to figure out what the heck went wrong. You can just run a small chunk of data on your local machine that looks just like the running process in the cluster, and you can actually easily get in to debug it and figure stuff out. And that's pretty cool, too. There's also some ability to get some insight into what's going on. Let's say you're trying to count the number of different kinds of errors. I'll probably take questions at the end. It's probably best. Let's say you're trying to count different kinds of errors or different kinds of conditions. You actually have distributed counters. So like each reducer can say whenever it has a problem rendering something or it can't follow a link or whatever, it can increment a counter. And at the end, you can get an aggregate sum of those things. because it's really hard to kind of know what's going on across 1,000 machines sometimes. And so by putting in the right kind of counters, you can usually get some sense of what's up. And these slides are totally stolen from Owen O'Malley, who works for Yahoo. Imitation, I suppose, is the sincerest form of flattery, and thank you. If you're thinking, gosh, MapReduce is really neat, can I try this at home? Well, unless you have 100 machines at home, it probably isn't so exciting. But Amazon has a big cluster you can pay to use, and maybe you do have 100 machines at home. And there is Hadoop, which is an open source implementation of GFS and MapReduce. And I believe they're also working on a big table implementation as well. So a lot of the tools you heard Jeff talk about are actually things you can start to play with now. And if you just search for this, you'll find it. They're seeing the same kind of insights. If you're trying to look at a really large data set and you're trying to process on one node, it takes too long. And if you're trying to process on 1,000 nodes, you've got a reliability problem. And so MapReduce solves those things. Again, they're basically duplicating bits of the Google system to do the same kind of work. So that's about how much it would cost if you wanted to play around with it on Amazon. It actually seems to be a pretty good system. I've talked to Doug Cutting, who's one of the guys who worked, I don't know if he's in charge of it, but he seems to be pretty important in the development of it. And it's actually scaled up to 1,000 nodes, and they've done sorts of 5 terabytes of data in a few hours. So it's reasonably mature. So if this is something you want to play around with and try running big distributed processes on, it's actually available for you to do. And I think that's good too. So to summarize MapReduce and why this is such a great thing, it basically simplifies machine allocation and coordination. The programmer just really doesn't have to worry about it. There are a few permission things you set up, and it just goes. It handles all the cross-machine communication. You're not setting up RPCs. You're not trying to figure out sockets, nothing. You just, you emit key value pairs largely. It handles the fault tolerance. Something goes down, it comes back, dandy. You go from 1 gigabyte to 100 gigabytes to a terabyte. As long as you can get permission from the guys running the cluster to use that many machines, hey, you're good to go. And the productivity thing is the intern thing that Jeff mentioned. It just makes it really straightforward to process large data sets. I'm going to take a really hard left turn and then maybe a right, and we end up here. I've been at Google about 18 months, and Google's a really interesting place to work. And a lot of the philosophy that goes into why we have MapReduce sort of comes out in the way we do things. Most devs work out of the same source tree. There really is one source tree at Google. And I had this disclaimer at the bottom, but Jeff saw this slide and he said, no, maybe I'm right, so we'll get rid of that. And actually, these are maybe valid observations. But all the devs work out of a single source tree. Does that strike anyone as surprising? I don't know. It strikes me as surprising. And mostly, it works. Mostly, the build isn't broken. Mostly, I can get the stuff I want. I say mostly because nobody's perfect, but it's not fundamentally inhibiting how I get things done. In principle, a dev can fix bugs anywhere in the source tree. So if there's something in Gmail that's really bugging me, and there is, you can actually just get Gmail, configure it, and make it. It's like 3 commands. I'm not kidding. It really builds that easily. The guys who make this stuff work are really impressive, and it makes it possible for Google to have, I think, 50 engineering offices around the world, because all the code lives in one repository. It's all written using a consistent style guideline. There's this 40, 50-page style guideline we have to read to write in C++ and get someone to agree that we understand it before we can start checking things in. OK, so in some ways that sucks, because you don't want to have to write in somebody else's style. I have the best coding style. I know this. But I'm willing to put that down, because when you get 1,000 engineers all writing with consistent style, it means that I can go into that code base and be like, oh, I understand that. I can track through that. He's not using exceptions in a funny way. There aren't any macros I don't understand. It's like speaking the same language. And that's huge. It really, really increases productivity. Code reviews are also mandatory for all check-ins. On Friday, we had something we needed to fix. And my office mate wanted me to OK this thing because we wanted to get it in for this push that had to happen. And I'm like, I can't. I haven't read it. And he's like, well, it's not even my change list. It's his. And we're like, OK, we can't check it in. We just don't do it, because it's not worth the cost of breaking the build for other people. You really try to work very hard to keep everything working all the time. We're also really serious about unit tests. So unit tests that run every night. If they fail, we get email, which is why it's good. They have good food there, because sometimes you're stuck fixing things when you break the build. But it works in the sense that there are thousands, I mean, tens of thousands? I can't even guess at the number of unit tests running every night to make sure that the software that people depend on across the company around the world actually goes. I guess the definition of night becomes kind of funny, because I think we're now more people outside of Mountain View than in Mountain View. I don't know what the whole world story is, but there's a lot of people. And these tools are shared company-wide. Like there's a small set of tools, MapReduce, Bigtable, GFS, and so on. And everybody uses them. And you're encouraged to use them. And if you don't use them, it's like, why aren't you using this? What's wrong with it? If you don't like it, fix it. If you need something new, build it and convince us why it's better. And this works really well. So we get these tools like MapReduce that are kept running by a team that really cares about making it happen. Also interesting is that Google project cycles are really short, like 6, 9 months is sort of a normal project cycle. I mean, you're shipping more often than that because you're just pushing things out. But like a major rev is maybe 6 or 9 months, not say 4 or 5 years, like some places. What? And devs change projects often. Like you're not expected to live on one project for your whole career at Google. Like, you know, if you're on a project for more than 2 years, something's kind of gone funny. Like you should be doing something else now. You should be getting different experience. And you're kind of encouraged to move around. So I think Google hires generalists rather than specialists, which makes sense because they've got to understand this entire source tree and be able to deal with it. And devs really own the stuff they ship in the sense that when we shipped the product I was working on, you know, related to maps, whatever, we had to carry pagers until the folks who run the clusters are like, OK, we trust you. Your code's good enough. And the pages went down and they took it over. So your feet kind of held the fire to make sure that it actually all works. You've heard about the peer-driven review process and flat management, so I don't need to go into those there. But there's a whole culture in this that's really interesting that plays into how these big tools work and how Google gets work done. And I think it's a part of how Google scales or will scale or is scaling. I'm not sure what the right verb is, but we're growing a lot and we still seem to be successful and we still seem to be building software even though we're adding engineers at the point where I'm 18 months in, and I think over half the people are newer than me. So questions at this point?
So if you need to run through MapReduce stages one after another, what do you use for intermediate results storage?
So do you mean if you have to run one MapReduce then another MapReduce?
Based on the first MapReduce.
Typically, yes. Yeah, almost always. You wouldn't. I don't think you would have to. You could use Bigtable as well. Sorry, I should repeat the question. I know better. What do you use? What does Google use for storage if you're running multiple MapReduces? And the answer is mostly GFS. You could be using Bigtable. I think it's possible to write to Bigtables during a MapReduce and read from them, but they're on GFS anyways.
Internally, within one MapReduce stage, do you use GFS as well?
If you're running it on your own machine, like if you're not out in the cluster, then it just reads and writes from the Linux file system, just fine. Yeah, pretty much exclusively.
Doesn't all these intermediate results have a lower GFS cluster?
What's the word you said?
Like, so you have a bunch of intermediate results.
Mm-hmm.
Is it a big load for GFS cluster to deal with intermediate?
GFS can handle it. No, it is. There can be a lot of data there, and so I'm sure people have looked at what could you do about chaining MapReduces together to be more efficient with the intermediate storage and to reduce the bandwidth between them, but it's not something that I know is actually being done yet. But yeah, there's some work there to do. A lot of the work in MapReduce is the moving the data around, and it's interesting to wonder whether most MapReduces are CPU bound or bandwidth bound. And I suspect they're bandwidth bound. And if you're running lots and lots of MapReduces, well, then you'd probably like to be a lot smarter about using that bandwidth. And right now, I don't think anything's being done to do that, but that's a good project idea. Yeah.
How similar is it to the internal GFS and MapReduce, and has Google contributed to that?
As far as I know, we haven't contributed to it directly, other than presumably through sort of intellectual background. I've not looked at the internals of the code, so I can't speak to that, but I have looked at examples of Hadoop MapReduces and sort of the way they structure things, and they look pretty much the same. I mean, if you squint, even their output screens look the same. They're not exactly the same. They do a slightly different way of defining what a collection of files is. We use like file name @20. They use a directory name, and it's all the files in the directory. 6 one, half dozen the other. So they're close, but not exactly the same.
What is the hardest problem, if there is a hardest problem, that you use MapReduce to solve in the Google Maps world?
Okay, the question was, what is the hardest problem that we use MapReduce to solve? Then he has to think to himself, can I answer that question? Probably I can't answer that question, but if you, it has to do with dealing with large graphs and doing processing in large graphs. That's a really tricky problem because it involves a tricky data structure. It involves potentially very large computations that use a large percentage of the data, as opposed to something which just looks at a single item or just a couple items. So I think that's some of the more complex stuff. I'm not sure, but I think some of the stuff that we're working on is probably some of the more complex MapReduces that are done anywhere because we're working on such sort of crazy data structures. It'd be interesting to try to go around the company and figure out, who's the badass MapReduce programmer? I don't know. Yeah. Okay, if you're running multiple MapReduces on a single machine, now is this like? Okay, so the question is, if you're running multiple maps on a machine at the same time, how does resource allocation happen? The short answer would be, I don't exactly know. The longer answer would be, I know there is a system which runs and jobs have priorities and it swaps things in and out. Sometimes your maps will get preempted by someone that has higher priority than you. If a map is waiting for data to get there, it will block until all the data arrives and other maps can run during that time. So there's sort of some friendly multitasking that goes on. Yeah, absolutely. And that's going to become more interesting as we have more cores.
Is the memory sharing policy like one task can use a lot of memory in queue or something?
The question was, is there a memory sharing policy? And yet you have to ask for how much memory you want to use. And if you blow that memory budget, then you get killed. And you go, increase your memory budget and do it again, which maybe isn't the most efficient thing to do, but it keeps you honest. In the back.
It's actually not a MapReduce question. I
Okay.
want to know if you could tell me a little bit about kind of the product design around Google Maps and sort of where the idea came from and kind of, not where it came from, but just kind of the culture in Google around the time you guys were releasing that product.
The question was, what's the story with Google Maps? Where did it come from? What's the culture around it when it was released? What's the sort of design process that went on? I wasn't there. That's sort of the short answer. I know how features happen now is, we built the system. It makes certain things possible because certain things get faster. I know it was vague because I can't talk about things. But you get the idea. Engineers realize we can do something that we couldn't do before. So we haul a UI person in and say, hey, we can do this thing, and we'd like to maybe have it look like this. And they're like, that's terrible. And then we go back and forth until we agree on what a really good design is. And then it gets added in some sort of sensible way. The bigger the change is, the more layers of bureaucracy you kind of have to deal with, which is kind of good because there are millions of users and you'd hate to irritate them all at once. I don't know if I answered your question successfully, but I'm glad I tried. How could you? Actually, you were first, I think, and then there.
So are there properties of the algorithm that actually would make it more incremental? And what I mean by that is, if you have a new road, right? There is a new road being built every day, or more than that in the US. Depending on how you actually do your MapReduce, can you actually rerun just the parts you want, or?
I understand what you're saying. The question is there a way of doing MapReduce in an incremental kind of fashion? Like if you get one more road, can you rerun things and not have to do the whole computation over? As I know right now, there isn't a way to do that. There are problems inside Google for which that's a really serious issue. And I know people are worrying about that sort of thing. So the way MapReduce is set up right now, it's not really designed to do that. You can imagine kind of doing it because you can think, OK, this is independent. It affects these things. You can keep like a providence chain or something that would figure it out. But I don't think it's implemented. Oh, sorry. Yeah, it was over there first. Sorry.
So it sounds like this is really good when you've got lots of sequential data to process, like when you're going to build the actual tiles for the map. But does any of this stuff help when the clients come to say, oh, I want to see this particular tile? Or is that just a really simple problem?
You keep the serving as simple as you can. Basically, the serving is like, here, take it. You don't want to have to do any processing. You don't have to look at the disk. You don't have to search around memory. You want to just barf out the cache data as quickly as you can. Otherwise, you can't get the kind of the turnaround that you want. If you remember, disk seek is like 10 milliseconds. You'd like query response to be like 30 milliseconds or something. You haven't got much time left. So I'm over there. And then, OK, I got to cut. So thanks very much. That was fun.
you.